By combining erosion and dilation, we can achieve different image processing techniques and algorithms. We are going to discuss some of them. One of the most remarkable are opening and closing. The opening operator is basically a erosion followed by a dilation. It smooths out the contours of the object, eliminating small saliences, and as we can see in this geometric interpretation here, as we can exemplify it or illustrate it by a translation of a structuring element inside the object. So in every position we can fit the structuring element inside the object that we are going to be opening. Then will be the result. So the result of all translations and intersections between the B and A. So if it removes spikes and transitions, in this case of the disk element, in the corners of the image. The closing is the opposite. So we first are going to dilate the object, and then afterwards we are going to erode it. In this case, the geometric interpretation is to shift and roll out the structuring element outside the object, and then everything that fits that does not fit this it is included in the result. So it is known by eliminating small discontinuities and small holes. Then it closes. For example, in this case, it smooths out the valleys of a shape. In the case of the opening, it removes peaks. This is an example of using opening and closing. We are comparing both. So let us take this image or this object A and then erode it by a disk B. So when we opening and closing it. So when we first erode it, note how we lose this connection between those two objects here. So we basically lose this gap between this bridge between them. And then when we follow the erosion by a dilation, those two objects are kept separated. So they kind of kept their sizes, the original sizes, while being separated. So in this for this case, for this reason, the opening is often performed to split objects that are probably by some chance connected in the image. In the case of closing, because we first dilate it, then we don't lose this this bridge between those two objects, and the final result is basically closing gaps, small gaps or shapes like that in the objects. So note how in the left hand side we kept this entrance here, and here it's gone, and this bridge here is gone here, but it's kept here. We can then combine morphological operators, not only opening and closing, but also erosion, dilation. In this case we have an fingerprint image, and we, in order to make it better because it is noisy, we can, for example, start by eroding it, follow this erosion by opening, and then dilate it back, and then closing the result. So we are using all of those operators, but we are, for example, in here looks like we are, instead of like doing erosion followed by dilation, we erode it, and then we open it, we dilate it, and then we close and then that's it. So we have an image here, resulting image that's not noisy as the first one. Finally, I'm going to show you the hit or miss transform. The hit or miss transform is a shape detection algorithm using a structuring element. So when we use this structuring element, let's say a D element, the erosion A with D can be seen as a set of hits in the image. Note that when we erode, we have to completely overlap D in A. So that means everything that fits, every position in which the shape in A fits D. However, only erosion cannot guarantee that the object will be disjunct. So we are going to use a local background information, a window containing the object. So let me show you, instead of showing the equation here, show you the example. So let's say we have this image here with two squares and one rectangle, and we want to detect only D, the structuring element D here. So we want to match or to see where in the image this specific square happens. When we first perform erosion, the result is this image here. So when we erode it, we left with 1 pixel in here, no pixels here because the object was too small. But for a larger object, it is as if we could fit many D structuring elements along C. So if we really want to retrieve just the exact object D, what we can use is a window, which is a structuring element that is basically a border of D. And then we perform the complete operation, which is the erosion first, which will retrieve all positions in which D fits in A. And then we are taking the intersection of this with the complement of A eroded by the window. So in this case, we are going to be left exactly with that point. I'm going to show you that in the Python code later. So modifying the notation, we can modify this notation and implement it in various ways. So we can use write D as B1 and B2 in order to split it. Then we can write in this shape here, so we can erode A with B1 and intersect with this B2, in which B2 is the actual W minus D. Using the difference and the dual relationship between erosion and dilation, what we can also apply is the erosion with B1 and take the difference with A dilated by the reflected version of B2. Those three equations represent the hit or miss transform. We can also apply the combination of erosion, dilation, opening, and so on to perform other image processing algorithms. For example, edge detection. Edge detection can be obtained by the difference of A and the erosion of A with some structuring element B. The filling algorithm can be also used. So we can, for example, consider A as a closed edge that is 8 connected. So let's say in here, this object here. So we have a border that is 8 connected. So every it is not open. So every value here 1 has a neighbor in the 8 neighborhoods, at least one neighbor on all values of the line. So here we have the complement of A and the structuring element. So we start with a seed point, which will start the filling. It is similar to that bucket operators that is common in many image processing tools, software, image editing software, such as GIMP, for example. So let us start with this point here that is inside the object, inside the border. And then for every value of k, we are going to erode the initial value, the initial element, and take the intersection with the complement of a. So note here, if I just dilate this this point here, I would obtain elements, all 4 elements. However, because I take the intersection with the complement of a, I just have those 3 ones here that are contained within the object. And then we keep doing that. So if we don't have any changes, we can just terminate the algorithm. But if we don't have, if 2 subsequent steps are not the same, then we do it again. Then we continue dilating it, and we are going to fill it until it is completely filled within. This operation is also called conditional dilation, because we dilate it, but we restrict it within some shape. And in here, this is the actual A union with the filling that we just did. We can also use the same idea to extract connected components. In this case, note that we are using similar, but we are not using the complement of A, because we want to actually extract how many what are the pixels that compose that object in total. So we are going to do that by taking the intersection with the actual object.